So I welcome you all in this course of Introduction to the Heat Transfer, a practical oriented approach, and today is lecture number 7, Newton's Law of Cooling. So in this lecture, Newton's Law of Cooling, we are going to see that how this law is applicable to the convection heat transfer. I once again going to recall your ideas about modes of heat transfer. So according to third lecture, the modes of heat transfer are conduction, convection and radiation. So for convection heat transfer, so that to happen that the basic idea behind the convection heat transfer is that this in any solid, if let's say let's once again take example of this metal rod. So this metal rod, if it is at a higher temperature, then if the air is flowing around this metal rod, which is having the air having a lower temperature than this metal, then the heat transfer will take place across the surface area of this metal rod, and due to the motion of the fluid particles of that air, so that is the convection heat transfer, and that convection heat transfer is governed by the Newton's law of cooling. So let's start the today's lecture objectives. So in this lecture we will understand a Newton law of cooling, okay, for convection heat transfer and its mathematical representation. We will explore some practical engineering applications regarding this Newton law of cooling with a convection heat transfer, and we will also compare this Newton law of cooling with Fourier law, the Fourier law which is we have used for conduction heat transfer. So we also have one simple numerical based on this Newton law of cooling. So what is mean by, or what is a Newton law of cooling? So basically the engineering definition, the rate of heat loss is proportional to the temperature difference between the object and its surrounding. What is mean to say here? Let's again take this example as a metal rod. If this metal rod is at 60 degrees Celsius, okay, and ambient air or the air surrounding to this metal rod is having a 10 degrees Celsius temperature, then the rate of heat loss from this metal rod is proportional to the temperature difference between this object or metal rod and the surrounding, which is air, okay. So in this case the heat rate is directly proportional to 60 minus 10, okay. So it is this law is applicable for both heating and as well as cooling, okay. And this law is depends on the fluid properties and the surface condition. These are the two main aspects of convection heat transfer we are going to see just right now. Once again we will repeat this example. So let's consider this is a heated rod which is at a 60 degrees Celsius temperature. First case is that the air surrounding to this is having lower density and lower temperature. Let's say the air surrounding to this is having 4 degrees Celsius temperature, and in second case water is flowing through to the surrounding of this heated rod, and that water is having 2 degrees Celsius temperature. Then the maximum heat transfer from this object to the surrounding is possible in the case of water which is having 2 degrees Celsius temperature. Why? Because the temperature difference is more in that case with respect to this object, okay. And surface condition, if this surface is rough or if this surface is well polished, okay, the surface roughness is the main important parameter in the convection heat transfer. So it describes this Newton law of cooling, it describes the rate at which the object exchanges heat with its surrounding fluid medium. Likewise, just I have given this example, likewise air, water and etc etc. In the practical example or in engineering application, we have came across engine operation. So in that engine operation, a radiator is used to cool down the engine, and that radiator is having extracted the heat from the engine, and it uses the basic principle of convection heat transfer. Okay, so we will see it in details in later. So core concept visualization: a hot object cools faster when the temperature difference is larger. Just before 2 minutes I have elaborated you a thing that in first case, let's say this hot object, okay, this hot plate, if it is at a 60 degrees Celsius, okay, and it is surrounded by a water, okay, a water which is at a 2 degrees Celsius or 4 degrees Celsius. And second case, this hot object or hot plate, metal plate, is at a 60 degrees Celsius but surrounding water is at a 20 degrees Celsius. Then the maximum possible heat transfer will occur in first case because it has temperature difference more, like this 60 minus 4, it is more temperature difference will be there, so there will be the more heat extracted from this object in first case. While in second case, this object which is having 60 degree Celsius temperature and the water which is having 20 degree Celsius temperature, the temperature difference is less as compared to the first case. So that's why in second case the heat extracted or heat transferred from this object will be lower. So cooling rate decreases as the object temperature approaches ambient. What is meant here to say? The same thing. The cooling rate or the heat transfer will decrease from this object when this object temperature approaches to ambient or surrounding temperature. Then there will be no chance of heat transfer. The basic idea behind this, in the first lecture we have seen that for heat transfer there must be a temperature difference or temperature gradient acted. If the thermal equilibrium achieves, then there will be no heat transfer. So the same basic idea behind the principle. Okay. So condition for validity. So this Newton law of cooling is valid for small and uniform object. So it is applicable or it is valid for small and uniform object. So there is no significant in internal temperature gradient. What is mean here? So internal temperature gradient, as in the case of conduction, here in Newton law of cooling there is no significance of internal temperature gradient. So why it is so? Because the convection heat transfer is governed by Newton law of cooling. Okay, and in convection we are not taken consideration internal temperature gradient. Internal temperature gradient we are taken into consideration in the case of conduction heat transfer. So keep in mind that the modes of heat transfer are three. First is a conduction, second is a convection, and third is a radiation. And how these modes are differ? First, in conduction, the solid to solid vibrational molecules that they are transferring the heat. Second, in convection, the fluid motion is a main motive or main primary thing that causes the heat transfer, and in radiation the electromagnetic waves causes the heat transfer. Okay, so these three basic things you have to keep in mind. So third condition for validity for Newton law of cooling is constant fluid properties. So why it is so? So let's take this metal piece as an example. So let's consider this metal piece is having three sections. First is this, second is middle one, and last is this one. So if this metal piece is at 60 degrees Celsius, if we consider this metal piece at a 60 degrees Celsius and surrounding air is at a 20 degrees Celsius, and if for this section the flow of air or density of air is more, and in between section the flow of air will be less, okay, we will consider this motion will be less here in this section, and at last section if the airflow will be higher, then how to calculate overall heat transfer through this object? So it will be difficult to calculate the overall heat transfer by the convection for this object. So that's why it should be valid condition, or the condition must be valid that overall whatever the fluid that means liquid or gases which is flowing over this metal having the properties to be same or uniform or constant. Okay, so surface convection is dominant. So in Newton law of cooling, the surface and the convection due to this surface is a dominant phenomena in this Newton law of cooling. So here one validity condition, the radiant dominant, whenever the radiation heat transfer is dominate over the convection, then this law is not applicable. Okay, similarly when highly unsteady environments are there, then here the Newton law of cooling is not valid. Okay, these are the two most important things. We have seen that in actual practices or in real condition, all of the three modes, conduction, convection and radiation, are together are acting on a same body for the heat transfer. Okay, but when in real condition the radiation effect of heat transfer is more than the convection, then this Newton law of cooling is not valid condition to apply for that example. Similarly, if the highly unsteady environment, likewise I just explained you, the velocity of air over the object is vary too much, okay, within this section, then that in that condition the Newton's law of cooling is not going to valid. So once again, just I have explained you. So heat transfer modes, just we have in conduction the governing equation is Fourier law and the conduction is taken place in between solid, okay, due to the molecular momentum and the free electrons. Also just right now we have seen convection heat transfer which is governed by Newton law of cooling and it is taken place between solid and liquids and these fluids are in a flowing state. Okay, radiation is electromagnetic waves is formed by or which is transferred by the electromagnetic waves, which we are going to see in the later lectures. So mathematical expression for Newton law of cooling is Q is equal to H into A multiplied by Ts minus T infinity, where Q is a heat transfer rate, its unit is watt, and H is a heat transfer coefficient which is having a unit of watt per meter square Kelvin, where A is a surface area, through which the heat transfer is taken place. Okay, and Ts is the surface temperature of that object. Okay, and where the T infinity is a surrounding air or any fluid temperature. Okay, so this is a mathematical equation, one simple mathematical equation, and we are going to see a simple numerical over this. So what is the physical meaning of these parameters? Larger the surface area and more implicates that more the heat transfer. It's simple is that in this equation you have seen that if this surface area will be larger, okay, or we can if we increase this surface area, then but obviously this heat transfer will increase because they are directly proportional. Okay, and higher the temperature difference, faster the rate. Just in before 2 slides I have explained that if the temperature difference between the object and the ambient air or ambient fluid is more, then it is more chances to have more faster rate of heat transfer. Okay, so convective coefficient H depends on the fluid motion and properties. So here H, where the H is heat transfer coefficient or convective heat transfer coefficient, which is mostly dependent on the ambient fluid temperature or properties or its stable conditions. Okay, so real world applications. So this Newton law of cooling is going to apply in real worlds such as electronic cooling, where the electronic devices are to be cooled by the fan and the fan is blowing the air. Okay, and that air having certain properties like density or temperature. So where there we have to calculate how much heat we have to be extracted. So that type of or that type of capacity of fan we have to install. So in HVAC system, what is mean by HVAC? Heating, ventilation and air conditioning system, which is used for comfort or thermal comfort of humans. So for thermal comfort of humans, we have to calculate how much heat to be extracted from human body for comfort conditions, and for that we need how much air or how much cool air we have to supply at what rate or at what velocity. Okay, so food and beverage cooling. So you have seen in a cold drink can that the flow of air or cold air in a refrigeration is to be designed, because if we put a cold air inlet, okay, in the refrigerator at topmost side, then it will have a better effect of cooling. So similarly here, a thermal comfort, which is same, we use this principle of Newton law of cooling in HVAC. Okay, so we are going to see how these cases are to be designed according to the Newton law of cooling or the convection heat transfer effect. So in this case, electronic cooling, the heat sink or the fan, just I have elaborated, this fan speed affect the H value. H means convective heat transfer coefficient, and this design consideration surface area and air movement. So the how the air movement should be and the surface area should be, that we have to design according to Newton law of cooling equation. That equation just we have elaborated here. Q is equal to HA multiplied by Ts minus T infinity, where H is a convective heat transfer coefficient, A is a surface area, and this Ts is a surface temperature of that object, and T infinity is ambient temperature, where the surrounding temperature, you can say that. Okay. Second is a HVAC system. So convective or convection between the walls and the rooms, and it is used for thermal comfort modeling for humans and helps in estimating cooling or heating time. How much time is needed for cooling, how fast the cooling or heating should be takes place. It is first, if you have to do the calculation to estimate the cooling time and heating time, first you must know that how much heat to be extracted, then according to that you plan the how much time is needed. Okay, and for calculating the how much heat to be extracted, you have to apply the Newton law of cooling. So what is the difference, or what is the main difference between the Newton law of cooling and Fourier law? So here I have mentioned that Newton law of cooling is governed for convection and Fourier law is governed for conduction. These are both different modes of heat transfer. So Newton law of cooling governs heat transfer between solid and fluid in convection. Okay, and Fourier law, the heat transfer within only solids. Okay, so driving factor, surface fluid temperature difference is a driving factor here, and here temperature gradient within the solid. Okay, so constant in Newton law of cooling, the constant is H, where H is equal to heat transfer coefficient or convective heat transfer coefficient, and in here Fourier law, the constant is K, where K is a thermal conductivity. So equation for this Newton law, Q is equal to HA Ts minus T infinity, just before we have seen this, and for Fourier law, Q is equal to minus K dt by dx, where dt by dx is a temperature gradient. So summary, Newton's law relates heat loss to the surface area and temperature difference and H. These properties are must for finding out how much heat to be transferred with the convection heat transfer. So easy to apply for preliminary estimates. So it is easy to apply where these fluid conditions are uniform, but in non-uniform fluid condition there must be some complicated equations with these use of the Newton law of cooling should apply. So useful in system design and control, just before we have seen that it is used for designing HVAC system, also electronic cooling system. So this Newton law of cooling basically is used for how much convective heat transfer should be takes place, and after that we have to calculate how much time is needed to extract or to cool down. Okay, so we are going to see one numerical example over this Newton law of cooling. So in this numerical, a hot metal sphere at 120 degrees Celsius is placed at a room, and the room is at a temperature 30 degrees Celsius. Its surface area is 0.5 meter square. The surface area of this metal sphere is 0.5 meter square. So the heat transfer coefficient with the surrounding air is 20 watt per meter square Kelvin. Here the 20 watt per meter square Kelvin heat transfer coefficient, which is H value. So what is the heat loss rate is asked. It is simply asked a Newton law of cooling. By Newton law of cooling, we have to calculate how much heat is dissipated or heat is lost through that metal sphere. So let's consider this as a metal sphere. So this metal sphere having surface area 0.5 meter square. Okay, and this metal sphere is having 120 degree Celsius temperature, and the surrounding where the room temperature is 30 degree Celsius. So how we can calculate how much heat transfer? Just by using the Newton law of cooling. So that equation is Q is equal to H into A Ts minus T infinity, where Ts is the surface temperature of that object, and where T infinity where the ambient temperature or surrounding temperature. So just putting these numerical values, where H is equal to 20, where A, which is the surface area of that object, which is sphere, is 0.5 meter square, and Ts, the surface temperature of that object, is 120, and T infinity where the ambient temperature is 30 degrees Celsius. Here the room temperature is mentioned. So just by calculating that, so 900 watt of heat are to be transferred to the surrounding at that moment. So from this object, 900 watt of heat is to be transferred to the room. That is going to be calculated by using Newton law of cooling. So have you get it? So thank you very much for today's lecture. So we will have 20 MCQs assignment over this lecture, and you will find lecture notes of this lecture in a PDF form in a discussion forum. So thank you very much.